to Liz.
Okay, great. Thank you, Liz, for the introduction. So, I'm sure all of us here are fully aware of just how important flight is to most birds. It's how they get around, and it's so important to their everyday lives. That's why if we want to understand anything about the lifestyle of birds, we have to find a way of quantifying how they fly. Now, for modern birds, this is quite simple. I mean, we can just look up and see how they fly, right? But for fossil birds, well, let's just say that things get a little bit more complicated. So this is where aerodynamic power curves, or APCs, come into play. Now, quite simply, all they show you is the theoretical amount of power that an individual bird needs to produce in order to fly at a certain speed, with the different interactions of drag creating the characteristic U-shaped curve. Now, if we then plot onto this the actual amount of power that a bird's flight muscles can produce, or the AP max, we can then begin to say some things about flight style. Now, the most fundamental concept, which is also the most important for this presentation, is whether or not the bird can actually fly at all. Because while the bird can fly at speeds below this maximum producible power line, it can't fly at speeds above the line. So quite simply, if the APC falls entirely above the AP max, the bird can't fly. Simple as that. So just to show you that this does actually work for modern birds, let's take a look at the APC for something that I hope we're all familiar with, a mute swan, very pretty bird. So this is an APC that I created earlier, and as I said before, the bird can fly at speeds anywhere below the red maximum producible power line. So that means that it can fly at speeds anywhere within this range. I can also tell you the speed that requires the least amount of power for the bird to fly at, the speed that the bird can travel furthest at, or its migration speed, and I can also tell you that a swan isn't very agile based on the relatively small power surplus that it has. Now, all of these stats that you've just seen are actually fairly spot on for a mute swan. So I'm sure you can see just how useful this could be if we could apply this back to the fossils. However, it's never really that simple in paleontology now, is it? So in order to find an APC, we need three measurements: body mass, the surface area of the body, or body frontal area, and the surface area of the wings, or wing area. And good luck getting those measurements from a fossil like this. Now, you're going to tell me that the solution to my problem is using a regression equation to estimate the variable that I want using a variable that I already have. Great, but there's one problem. See, there's an inherent amount of error associated with regression equations that must always be taken into account. Whoops. And the way that we normally take this error into account is through confidence intervals. Now, confidence intervals show you how close your estimation will be to the sample mean or the regression line. And this is a problem because our sample can only be made up of modern birds, so we can estimate the desired variable and the known variable in the first place and actually create our regression equation. However, as we all know, fossil birds do not necessarily have a modern analog. So that means that the true values of the fossil birds might not lie anywhere near this regression line showing you our sample mean. So that means that confidence intervals are out because they might not actually cover where the true values of the fossils lie. So what we need instead are prediction intervals. Now, prediction intervals are very similar to confidence intervals, but they're wider. Now, they're wider just because they cover 95% of the data points within the sample, and not just the sample mean. So that means that if you've constructed your data set well enough, then these should be representative of the entire population of birds. And then maybe, just maybe, it might also cover where the true values of the fossil birds lie. So we're already increasing the amount of error by having to use prediction intervals instead of confidence intervals. But that's not our only source of error, of course not. So the other source of error comes from the power equation that we have to use in order to calculate the APC in the first place. So the problem that we have here is that body mass is squared, and then both body frontal area and wing area are then added on top of this. So what you have is the errors from multiple different estimations being combined all in one equation. And this is a phenomenon known as error propagation. Now, error propagation has its own specific set of rules that you have to follow, telling you how to combine the errors from multiple different elements when they're all in one equation. And let me tell you, it's not as simple as just adding them all up. I really wish it were. Instead, there are a specific set of formulae that you have to follow, there are a specific set of formulae that you have to follow depending on the mathematical signs and power levels within your equation. And overall, this increases the amount of error present, because of course it does. So we have two sources of error, one from the regression equations and one from the power equation in the form of prediction intervals and error propagation. So the real question is here, is this actually too much error? Is there so much error associated with calculating an APC using regression equations created from modern birds that they just become completely unreliable? Well, in order to answer this question, I trawled through the internet, trying to find as many regression equations as I could and data sets as I could for body mass, body frontal area, and wing area. And then from there, I calculated their prediction intervals. So in order to compare all of these prediction intervals and see which one is the narrowest, I decided to find the relative width of them by calculating the percentage difference between the upper prediction interval and the regression line. I then used this value to find the narrowest prediction intervals, i.e. the regression equations with the least amount of error, to give this the best chance possible. And then once I'd done this, I calculated some APCs and incorporated the error from the prediction intervals and the error propagation rules into them. So in order to see what the result was, let's go back to our mute swan. So this is the same chart that I showed you earlier, with the solid blue line showing you with the solid blue line being the APC that I calculated directly from the regression equations, and this range representing the error margin. Now, what I want to draw your attention to is just how big this error margin is. So theoretically, I can have an APC light anywhere within this error margin, and it would still be a valid result. I mean, I could even have an APC light all the way up here, above my red maximum producible power line, which would mean that my swan couldn't fly at all, which is obviously a bit ridiculous. I mean, obviously swans can fly, right? Well, yes, but can you really say that for something like Archaeopteryx? Not with any certainty. And lo and behold, if we look at the APC for Archaeopteryx, we have a very, very similar problem, whereby the upper limit of the range within which an APC can lie is way above my red maximum producible power line, so basically this means I can't tell you anything about the flight capabilities of Archaeopteryx based on this graph. I got nothing. So at this point, I was almost ready to throw in the towel and just storm off in a rage. But then I calculated the APC for this specimen. So this is Salmilla robusta, which is a Middle Eocene crane-like bird, and this is its APC. Now what's interesting here is that our upper limit is really, really close to our maximum producible power line. I mean, it's not below the line, but it's getting there, which made me think, why is the error margin so different in this sample compared to the other samples? Well, in order to answer that question, I decided to find the relative width of the error margins as the percentage difference between the upper limit of the range within which an APC can lie and the APC itself. And then I correlated that value against my morphological variables, as in body mass, body frontal area, and wing area. And this was the result. Now what's interesting is that every single one of the morphological variables is strongly and significantly related to my range width. In particular, though, body mass has a particularly strong correlation. So why would that be? Well, if we go back to our power equation, we can see why. So as I said before, body mass is squared. On the other hand, neither body frontal area nor wing area are raised to any power. So that means that any error associated with estimating body mass is going to be translated much more strongly into our APCs, and is essentially the main reason for this massive error that's happening. I mean, body frontal area and wing area also have an impact, but it's nowhere near as large as the impact that body mass has. So that got me thinking, if I find a small enough bird, can I reduce the error margin enough to create a vaguely reliable APC? Well, let me introduce you to the Ruby-Throated Hummingbird. It's a very small bird. In fact, it only weighs 2.8 grams. And this is its APC. Again, this line is above this line. Quite simple. So if I can't reduce my error margin enough for something this small, it's unlikely that I'm going to find any bird that's small enough to create a vaguely reliable APC, especially in the fossil record, due to the poor preservation potential of birds in general, never mind something that tiny and delicate. So going back to my question before, is there too much error associated with calculating an APC using regression equations from modern birds? Yes. Quite simply, just yes. But this is an issue that I've seen quite often in paleontology, whereby I know people, so say for example, let's take me. I don't have much of a background in statistics. I knew nothing about these errors before I started looking at them. And I think that's an issue for quite a few people here. So please, 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 no matter what statistical analyses you do, there's always going to be error associated with them. So please take them into account. Otherwise, you may end up misinterpreting your results or coming to conclusions that you may not have come to otherwise. So, are there any questions? That is it.